we're live. Okay, so organic chemistry, chemistry of carbon, except, surprisingly, except carbon dioxide and carbonates. Okay, we don't put these into... Oh, Zara's arrived at last. Okay, we don't. These aren't classed as organic, strangely enough. Carbonates and carbon dioxide, but that doesn't really affect us. It doesn't affect us at all. So it's the chemistry of carbon. Now it's such a vast field. It's enormous. It's an enormous field, and it covers all the molecules of life. Molecules of life. So it covers what we call biochemistry. All right. So as you can imagine, there's a vast amount of biological molecules, and that's what organic chemistry deals with. All right. So let me get a different color. I don't like green. All right. So because it's so big, because the field is so big, what do we do when we have anything big? Some people have asked me to say, yeah, we're recording it. Don't worry about it. Do you still hear? Yeah, we're recording it, Zara. Don't worry about it. Okay, so because it's so big, because it's so vast, what we do with anything vast, we split it up. So we split it up into smaller chunks. Oh, how do you spell chunk? Something like that. We split it up into smaller chunks. And these smaller chunks are known as homologous series, which you may or may not have heard of. Okay, so these are the small chunks that we split organic chemistry into, homologous series. Now, there are 4 homologous series we study. There's thousands of homologous series, but we only study 4 of them, okay? And the first one, the last one, let's put it, sort of organize it if we can a little bit. There's one there, and there's one there. The first one we study are called alkanes. My pen's really weird today. I wonder why. I wasn't doing this earlier. Alkanes. Let me write that again. It's writing really thick. I don't know. Maybe it's some internet problem. Alkanes. Next one are... Let's use a nice blue one. Alkenes. Next ones are alcohols. And the last one are... Let's give it its proper name. These are known as carboxylic acids. Carboxylic acids. Okay, in biology they call these the fatty acids. All right, so that's what we do. We split up organic chemistry into 4 bits: alkanes, alkenes, alcohols, and carboxylic acids. All right, so alkanes, what are these? These are made of carbon and hydrogen only. This is an example of an alkane. Okay, and an alkene is made of hydrogen and carbon only. So these 2 things, alkanes and alkenes, because they're made of hydrogen and carbon only, these are known as hydrocarbons. Okay, and the big difference is this. Let's get a nice blue pen. Alkanes have only single bonds, whereas alkenes have double bonds. Double bonds between carbon atoms. Okay, as you can see, this one's only got single bonds. This one has a double bond. All right. Now, because they have only single bonds, they're known as saturated. And saturated means you can't get any more stuff on it. You can't get any more hydrogens on. Why not? Because all the bonds are used up and there's only single bonds. Whereas alkenes, because they have a double bond, are known as unsaturated. Okay, so alkanes, these guys, are known as saturated hydrocarbons. Whoops, Tamia. Alkanes are saturated hydrocarbons, whereas alkenes are unsaturated hydrocarbons. But they're both hydrocarbons. They only contain hydrogen and carbon. Okay. All right. Next one is alcohols. Now, let's draw which colour shall I use? Oh, I've got 2 blues there. All right. So let's draw an alcohol. Alcohol looks like this. they're saturated, by the way. Okay, so far it looks like an alkane, but then we have a group, an OH group on there, and this is an alcohol. All right, it's obviously not a hydrocarbon because there's an oxygen in it, and the last group is the carboxylic acids. Now these look like this. These are the hardest structure to draw. Okay, now if it's got this group, it must be an alcohol. If it's got this group, it must be a carboxylic acid. All right, or an organic acid, they're often called. Organic acid. All right, now if it's got this group, the carbon-carbon double bond, it must be an alkene. And if it's got nothing, this one has nothing, I'm afraid. There's nothing here. All right, it's just carbon and hydrogen. It must be an alkane. Okay. Now these groups I've highlighted here. This group here, the double bond, the OH group, and the COOH. These are collectively known as functional groups. Okay, so these are functional groups. So what's the functional group of an alkene? It's the C11C. What's the functional group of an alcohol? It's the OH group. What's the functional group of a carboxylic acid? It's this COOH group. Okay, so these are the 4 homologous series we study, and that's it. Now, before I go on, I've been talking for a long time. Any questions so far? I'm recording, by the way. Let's move this up. Any questions? If there's a no, just type in N, so at least I know I can go on. Anyone? Anyone? Anyone at all? All right, I'm going to assume everyone's good if I don't hear anything. All right, so let's do them in order. The first one are alkanes. And as we've said before, these are saturated hydrocarbons. And this bit, as I've said before, means contains only single bonds. And this bit, it means it contains hydrogen and carbon. And the last word is the most important word. Only. If you don't say that, you won't get any marks. Okay? So these are alkanes. Okay? Now the simplest alkane, well, we've got the same colours. Right, the simplest, let's go back to green. The simplest alkane has 1 carbon. Okay, and there it is. There's 1 carbon. The next one along has 2 carbons. Okay, the next one along has 3 carbons. Okay, we'll go up to 5 carbons. Next one along, let's do these down here, has 4 carbons. And one thing you've got to remember about organic chemistry is carbon has 4 bonds, and you must remember that. And the next one has 5 carbons. Okay, and they're all just like this. They get longer and longer and longer. Okay, we're not going to go for the longer ones. Okay. So there are the first 5 members. First 5 members. Okay. And, well, let's have a look at them. Right, now, what are these called? Let's try and name them. Actually, before we name them, let's try and do the formula. So this first one is CH4. This next one is C2H6. The next one is C3H8. The next one, oops, I'm missing a carbon there, a hydrogen. Next one is C4H10. Next one is C5H12. Okay, and one interesting thing is one member differs by the next one by just a CH2. Okay, so let's draw that in purple. So we add a CH2 and we get the next one. We add another CH2, we get the next one. You add another CH2 and another CH2. They grow by CH2 each time. Okay, now this is the formula of the first one: C4H8, C2H6, C3H8. Sorry, CH4. I don't know what I'm saying. CH4 is the first one, C2H6, C3H8. Now, if you're good at maths, you can see that these actually can be represented by what we call a general formula. Does anyone know what the general formula of alkanes is? Very quickly, I'm trying to get you involved in this because no one's asking anything and I'm falling asleep here. Anyone? What's the general formula of alkanes? Well done, yeah. Yes, CnH2n plus 2, that's right. So it's CnH2n plus 2. Okay, as you can see, how does it work? Well, if n is 3, we get the third member. And the third member must be C3. H, 2n is 6 plus 2 is 8. And we get this one, don't we? Yeah? All right, so that's what we mean. These alkanes can go enormously, right? Any plastic you've used can easily be 120,000 carbons long. All right, that's not a very long one either. These get enormous. So we only look at the first ones, the simpler ones, okay? So if I asked you what is the 58th member, what's the formula of the 58th member? You would say, anyone know? I think I've worked it out in my head. What's the formula of the 58th member of the alkanes? Anyone? C58H, I think it is. Yes, it is. It would be C58H. Well, 258 is 116 plus 2, 118. Okay, simple as that. All right, so there you go. So the 58th member would be that. And it would be called something like octapentadecane or something. I don't know. But they get their names get much more. They get quite confusing as you go along. Okay, so these are the formula of the first 5. The next thing we'll look at is what are their names. Well, their names come in a couple of flavors. First of all, because they're alkanes, they must end in ane. So all of them are called ane. Something ane. Okay. Now, the first member, it gets the prefix, isn't it? The bit that starts meth. So the first one is methane. Next one is ethane. Next one is propane. Next one is butane. And then this last one is pentane. Okay, so there you go. We've got the names, we've got the formula, we've got the structures. Okay, now any questions on that stuff so far? So far, not particularly hard, but it is just an introduction to organic chemistry. Are we all good? I'm sure there's nothing really interesting so far. All right, there is coming up though. There's something coming up in a minute. Okay, now, so we've got the formula and the names and the structures. However, if you've got one carbon, all you can get is methane. There's nothing else you can do. If you've got 2 carbons, all you can get is ethane. There's nothing else you can do. If you have 3 carbons, believe it or not, you can only get one structure. Okay, and there it is. Okay, now it is possible to get this. Okay. But does this have the same formula as this? Can anyone see? Anyone see that? This one, let's call this A and B. Do they have the same formula? The answer is, as no one else is playing along. Yes, thanks, Eric. Eric, you're the only one. Is everyone else's computer broken or something? All right, these aren't the same. So even though it looks like, oh, you can draw this one is wrong. Okay, we can't draw this. This is not the same as the other one. Okay, this one is C3H6, the other one is C3H8. So this is wrong. Okay, so the first 3 members, there's only one formula. There's only one structure you can do. But after you get to 3, 4 and above, you can get more than one structure. Okay, all right, and now let me try and draw these. My internet's very flaky. Everyone must be streaming the West Ham game. That's all I can assume. All right. So let's get rid of this rubbish. So let's draw 4. Now this one here, let's do this nice green. This one is C4H10, but you can also get this. Now if you look at this, if you count the hydrogens and the carbons, it's also C4H10. So C4H10 can exist as 2 forms. It can exist as this one. They're both C4H10 and this one. So this one and this one. Now, when that's possible, when you get, and it is possible, when you get something with the same molecular formula, but different structures. Does anyone know what we call that? When we have the same molecular formula, but different structures. Since no one's playing along tonight, are they? What do we call that? Well, I'm trying to pick a pen here. Let's pick this colour. If they're the same formula but different structures, we get what? Anyone know? Oh, yeah, it's called isomerism. These are known as isomers. Isomers. Okay, iso means the same, mer is parts. So these have the same parts. That's what the Latin is anyway. All right, and it's the same formula, different structures. Now, butane can be like this, and this is a form of butane. Now, we don't have to know this at IGCSE level. Trust me, you don't. Okay, so let's get a nice pen. Oh, we haven't used that colour, have we, before? But this one is called butane, the one at the top. But this one, well, what do we call this one? Well, this one looks like propane, doesn't it? So we call this one propane. But there's something on my propane. And what's on my propane? Well, it looks a little bit like methane. Okay, that's on my propane. So this guy is called methyl propane, this one. And they're the only isomers of butane. C4H10 is butane and methyl propane. I'm not going to go into this. Let me go to point 2 because that's a bit nicer. All right, I don't want to talk about this too much, but this normal one, this is actually called N-butane, and N stands for normal. So there's 2 isomers of butane, N-butane and methylpropane. All right, there's the same molecular formula but different structures, and they're the only 2. Now, pentane, I think, off the top of my head, I think it has 3 structures. So you have the straight one, N-pentane. Okay, this is N-pentane, which is C5H12. Okay, that's the first one. Okay, what else can you get? You can get 1, 2, 3, 4, and 1 coming off it. Now, does anyone know what we might call this one while I'm drawing it? Try and guess what this one is called. What's this one called? This first one, this one is called pentane. But what's this one called? Anyone want to guess? Anyone at all? Bloody hell. It's not, no, it's definitely not pentene. It's got to end in ane. It's an alkane. It's still unsaturated. Sorry, it's still saturated. Thomas and Eric. It's still saturated. It's still a hydrocarbon, so it's still an alkane, so it can't end with ene. It's going to end with ane. What did I do with methylpropane? Do the same trick as I did with this. Methylbutane, exactly. Oh, not butene. Why did you say butene? It's this. Yeah, butane. It's butane. That's butane. And there's a methyl stuck onto it. So we call it methylbutane. Now, if you wanted to be really posh, okay, which carbon is it attached to? Can anyone? Yeah, of course it is, Azim. Which carbon is it attached to? The methyl. Now, what we do, we number, yeah, exactly, Thomas. We number the carbons. 1, 2, 3, and 4. Okay, we number them, so the dangly thing, this thing here, is attached to the lowest number carbon. So if it's attached to this one, I start counting from this side. So it's attached to number 2. So the posh name for this is actually 2-methylbutane, okay? Because the carbon is on number 2. All right, now let's push this up a tiny bit. Is this helping? Am I helping anyone? Because when you're all quiet, it's like, oh God, they know this stuff. Is this helping anyone? Oh, Eric, you're just being sweet. Zara, you've spelled your name right. Well done. Right, so we get pentane and 2-methylbutane. These are isomers of pentane. And there's one more. There's one more pentane. Whoops, let's do the same color. If you're very, very clever, you'll see the third one. It's 1, 2, 3 in a row with one up there and one down there. Okay, so let's put my hydrogens in. Okay, and if you look, I'm sure you can figure this out, but if you calculate the carbons and the hydrogens, they're all, oh, there's a hydrogen missing, they're all C5H12. So these three here, these three guys here, there are three isomers. And there's only three isomers of pentane. There's two isomers of butane. There's three isomers of pentane. There's no isomers of methane. There's no isomers of ethane, and there's no isomers of propane. As you get longer, you can get more structures. That makes absolute sense. Okay, so there's only three isomers of pentane. All right. Now, for extra credit, anyone think they're going to have a guess at the name of this guy? This is a nice compound. It really is. It approximates a sphere, by the way, which is a real shame because we will never know, will we? Because unfortunately, on this planet, we teach each other on flat surfaces. So we all think things are flat, but they're not. This is three-dimensional shapes, and they're quite beautiful. If any of you are interested in going into designing drugs, for pharmaceutical companies, you have to know. Have to know the shapes of things because you have to know how they fit into body, enzyme crevices and stuff like that. So knowing the geometry of molecules is really important. Anyway, does anyone want to guess at what this guy is called? The third isomer of pentane. Anyone know? Does anyone know? Oh, yeah, dimethylpropane. That's a pretty good guess, I'll tell you. Well done. Let's start. But I can't beat that. That bit is propane. There's a methyl on my propane. But there's another methyl on my propane. So we say dimethylpropane. And the only thing, Azim, is which one are they connected to? Which carbon are they connected to? Anyone want to guess? What do you think the two methyls are connected to? No? Yes? Well done. So one of them is connected to the number 2. What's the other one connected to? Anyone? One's connected to number 2. The other one is connected to... The other one is connected to... Everyone's being cheeky. Everyone's a chicken. The other one is connected to number 2 as well. Okay? So this is actually called 2,2-dimethylpropane. Okay? Because this one is number 2. And this one's connected to number 2, and this one's connected to number 2. So we say 2,2-dimethylpropane. Okay. Now for fun, 1, 2, 3, 4, 5, 6. I'm going to put one there and one there. Okay. What's this called? I'm going to slowly fill it in, and your job is to tell me what we call this monster. Well, there's a lot of hydrogens here. I tell you, the bane of an organic chemist's life is drawing hydrogens. There's so many hydrogens. What do we call this monster here? Anyone? It's good fun naming these things, but it's not vital. What do we call that thing? Either the internet's rubbish or there's no one there. Anyone? Azim, you're good at these. What do we call that? If you don't know, say IDK. Oh, yeah, I know what that means. Oh, well done. Shad. I think I'm sorry if I'm mispronouncing it. Yeah, but you're so close. Oh, well done, Tiso. Well done. Let's have a look. It's so easy, isn't it? Really. This guy here. What is this guy called? Well, let's count. 1, 2, 3, 4, 5, 6. So this is called hexane. There's a methyl on my hexane. There's another methyl on my hexane. So this is dimethylhexane. And which numbers are they on? Well, I'm going to call this one number 1, 2, 3, 4, 5, and 6. One of them is on number 3, and one of them is on number 4. So that's the name of it. 3,4 dimethylhexane. Now, let's have a look. Let me see if I can copy that. I'm doing some weird stuff on the internet now. Don't worry about it. 3, 4 dimethyl. Oh, that's a weird one. I'm getting up. Dimethylhexane. Okay, and I'm just seeing if I can Google a picture of it. Oh, that's annoying. But there's a lovely picture here, but they're a tiny bit confusing for you guys. But let's try and see if I can snap it for you. All right, let me grab the picture. Whoopsie daisy. Right. Unfortunately, it's doing some weird stuff. It's got how we draw it at A level is basically what it is. Oopsie daisy. Let's try again. Let's do the snipping tool. All right. All I'm doing is I'm going to the internet. I'm trying to find a nice picture for you. All right. There it is. And now let's zap it over here. All right. Sorry it's taking so long. These take forever, these things. These clips. You can probably hear my mouse clicking. All right, is that the one? Let me put. I can't remember which one it is. Is that the one? No, that's not the one. I didn't label it nicely, did I? Right, get rid of this. Don't worry, we'll be normal surface will be resumed. There you go. There it is. Okay. Now this is how we write it in A level. It's a bit of a weirder way. This one. All right, but that's what we do. Okay. So. This is 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons. So that's the hexane bit. There's a methyl on number 3, the methyl on number 4. Okay, so there you go. That's how we get that. All right. Okay, so we've done with the alkanes. We've done the chemical properties. Now there's some interesting. Sorry, we've done the physical. No, we haven't. We've done the structures, haven't we? But all we've done so far is looked at how we draw them. And believe it or not, I know you won't believe this, but the hardest thing about organic chemistry at IGCSE level is learning how to draw the things. I promise you. If you can draw them, you're fine. All right, seriously. Okay, so let's have a look at the first 4 or 5 members. So the first member, as we've seen, these are alkanes. We haven't done anything with the alkanes yet. We've just looked at the structures. So the first one is methane. Next one is ethane. Next one is propane. Next one is butane. And next one is pentane. Okay. Obviously, meth means 1. Eth means 2. Prop means 3. But means 4. And pent means, pent means 5. Okay, so this is CH4, C2H6, C3H8, C4H10, C5H12. Okay, these are the first members. Now, what's the state at room temperature and pressure? Methane is a gas. Ethane is a gas. Propane is a gas. Butane is a gas. Pentane is a liquid. Okay, if we went on and on and on and on, you go liquid, liquid, and then if you go on and on and on and on, they become solids. So from that we can deduce the melting and boiling points of these guys. As you increase the number of carbon atoms, the melting and boiling points increases. Okay, and that's a very important trend. So as the number of carbon atoms increases, why do we crisscross represents carbon? Azim, don't worry about it. They're called skeletal formulas. All right, don't worry about that. It's just an advanced way of doing it. Okay, we often do this. So, what's that called, Azim? Have a guess. What's that? That funny thing there. Anyone want to guess what that's called? This is called skeletal formula. You don't have to know this, but it's kind of fun. Anyone? No, 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 no. This guy? No, it's actually 6. 1, 2, 3. Oh no, you're right. It's 5. Oh dear, it's embarrassing. It's pentane. Yeah. What about this one? What's that called? Azim, you're good at these. What's that weird one called? It's shape of a hexagon. Yeah, it is. Well, it's not quite hexane. Hexane would be this: 1, 2, 3, 4, 5, 6. That's hexane. So this is hexane because it's got 6. But this is also hexane because it's also got 6. But they're obviously not the same, are they? But this one here is arranged in a kind of circle shape, so we call this one cyclo. It's called cyclohexane. All right, very good solvent, cyclohexane. We've got some at school. Anyway, so characteristics of an homologous series. And the first series we're looking at is alkanes. But the characteristics of homologous series are all pretty much the same. Number one characteristic, they can be represented by a general formula, as we have seen. And what's the general formula for alkanes? It's CnH2n plus 2. Okay, they can all be represented by a general formula, but we're just looking at the alkanes. But that's all homologous series do this. Number two, each member differs from the previous by... Does anyone know what I'm going to say here? This is a strange property that very few people talk about. But each member differs from the others or the previous one by what? What does it differ from? Or how does it differ from the previous one? Does anyone know? Anyone remember? I've mentioned it. No? Anyone? We'll stop in about 5 minutes. Eh? I don't want to go too long. Does anyone know how they differ by? Which each member differs by from the previous one by what? This is in all homologous series. They differ by a CH2. Yeah, well, no. One from the other differs by a CH2. Alkanes, one alkane to the next alkane, the difference is a CH2. One alcohol to the next alcohol is a CH2. One carboxylic acid to the next carboxylic acid is a CH2. They all differ from one member to the next member by a CH2. That's a characteristic of a homologous series. Number three, what's another number? Okay, well, crazy but true. I've just drawn it down here. Okay, as the number of carbon atoms increases, what increases as well? MP and BP increases. Okay, we could do, that's all you need, by the way, for any exam at this level. But we could do number four. What do you think happens as you increase? This is an obvious one, really. But if you keep on increasing the number of carbon atoms, what do you reckon happens to the density of these things? Does the density increase or decrease? Would you reckon? Very quickly, as I go from smaller molecules to larger molecules, what happens to the density? No one's saying anything, so I'll tell you. As the number of carbon atoms increases, the density increases. All right. This is a very common question. That's why I'm doing this. They'll often ask you, give three characteristics of homologous series, and these are the easy ones, aren't they? So they can be a general formula. They differ by CH2. As the number of carbon atoms increases, the melting and boiling point increases. The density increases as we go along. Number one, then this is a useful one as well. The solubility in water actually decreases. As they get bigger, they become less and less soluble in water. They're not soluble anyway, but they get less soluble in water. I think, number six, they show similar chemical reactions. Okay. And all I'll do now is we've nearly done. We've just done some physical properties of the alkanes, but this is pretty boring stuff, to be honest with you. We've done organic chemistry is lovely, but we've got to wade through some of the weeds to start with. But that's pretty well all the physical properties. So I'll do one chemical property. There's only two chemical properties, by the way, but let's just do one and then we'll call it a day, because I don't like these videos going above 40 minutes because that's a normal lesson, isn't it? So we're still doing alkanes. Okay, but we're nearly finished though. Shows that there's not much that really there, is there? Alkanes, but they take part in two types of reaction. One of them is called combustion, and the other one is called substitution. So how do you know substitution? Substitution. Okay. Now, because they're good at burning, they burn. Okay, and when they burn, they give out lots of energy released when we burn these guys. And that's why they're part of the petrochemical industry. These are our fuels. This is where we get petrol from. Petrol, diesel, fuel oil, all the butane, cooking gas, all the gases. Everything we use basically for energy in the home are burning alkanes. That's what we do. Substitution, this one is a bit more complicated, but we won't do this today. So we'll leave this for now. But when we combust them, okay, an alkane, and this is always true, if you give it enough oxygen, it will burn, they'll burn, and they'll always form. If you give them enough oxygen, you'll always get carbon dioxide and water. Okay, so if you give them enough oxygen, we call this complete combustion. Okay, but crazy but true, if you have an alkane and insufficient oxygen, anyone know what we might get then? This is known as incomplete combustion. Anyone know what we get if we have incomplete combustion? Anyone? No? I'll do it. Oh, yeah, well done. We get combustion. Right, we get a load of stuff. We can get carbon, believe it or not, on its own. Isn't that creepy? You can also get carbon monoxide. You can still get carbon dioxide. You still generally get water, I must admit. Now, this is a nasty gas. Okay, and it's called carbon monoxide, and it is poisonous. Okay, what do you reckon we call that when something? Oh, well done, Eric. You're quick. Yeah, soot, and that's what the blackness. Now, if you put your finger in the exhaust of a car, don't do it when the car's running. But if you put your finger in the exhaust of the car, you'll get soot on your hand or your finger. And that's because of incomplete combustion. All right. So you get carbon monoxide, you get soot, which is pure carbon, you get carbon dioxide, and you get water. You'll never get hydrogen. The hydrogen always manages to get its oxygen. If there's any oxygen around, the hydrogen gets it. Okay, so you'll never end up with pure hydrogen. Now, there's the last thing I want to say here then is this. I don't know what kind of house you live in, but in the old days, this is a window of a house. This is your house window. Okay, and this is your house. All right. And there's your window. I don't know. These days it's not very common, but above the window there was a funny brick, and it had these 4 holes in. Does anyone live in houses like this? If you do, it's probably an older house. Okay, but have you seen these bricks above windows? Yeah, they've got 4 holes in. Has anyone seen them? You don't. There's nothing wrong with living in a house like this. It just means they're older construction. But have you seen those bricks above a window in a house? Has anyone seen it? Oh God, this is painful. No one's answering anything. You haven't seen it, Eric? Yeah, we get these. These are called air bricks. What do you think they're for? Yeah, you do get them in the village. You do, exactly. All right, you get them in some. If you look at older houses here, you get them. They're known as air bricks. Okay, and you know why they're there? Because exactly, Azim. In the old days, people used to burn paraffin heaters inside the house. Yeah, I don't know how many holes, Eric. I've seen the ones around here have 4 holes anyway. So they're called air bricks. So they're to allow oxygen in because people used to die in their houses. They used to, cook with paraffin, and they used to heat their houses with paraffin, and you get a buildup of carbon monoxide, and people would die. So these used to be in the building code. All right, it wasn't. You didn't have a choice. you had to include air bricks into your house, and that was to let oxygen into the house. Now, the thing about carbon monoxide poisoning, the bad thing is, it's painless. Isn't that sad? So you're sitting at home and you just feel sleepy, and that's it, guys. Game over, right? So these air bricks were introduced into the building code. All right. However, a very last thing. I know I've gone on a little bit too long. All right. I think these days, I think that who uses paraffin in the house these days? Yeah, not many people I know. I must admit. You know what I mean? In the old days, you used to use these heaters. When I first arrived in Botswana, I had a paraffin heater. It was really nice and warm as well. Um, and people cooked with paraffin. These days, we use butane, don't we? Tend to use gas. But in those days, we used paraffin, and you get the buildup of carbon monoxide really quickly. All right. Anyway, let's do an equation now. Let's say C2H6. Let's balance the equation. I'll show you how I balance these equations, and then we'll call it a day. There's C2H6. It's going to react with oxygen. You're going to get carbon dioxide and water. Okay, so I want to balance this equation. How am I going to balance it? This is how I do it. Okay, 2 carbons, so there must be a 2 there. 6 hydrogens, there must be a 3 there. And now I ignore this and I go to the right hand side. 2 times 2 is 4 oxygens, 3 oxygens there. So in total, there's 7 oxygens here, aren't there? How do I make this 7? I make this 3.5. 2 times 3.5 is 7. So as it stands, this equation is balanced. But it's not right yet. What do we do to make it perfect? Does anyone know? I hope you saw how I balanced that. You just jump over the oxygen and find the oxygens on the right-hand side. All right. Anyone know how we balance this? It is already balanced. Yeah, exactly. We times everything out by 2. So we say 2 of those, 7 of those, 4 of those, and 6 of those. Okay, it's very easy, but when you ever do an equation like this, you must balance them. All right, now we've done 46 minutes according to my clock here. We'll call it a day there. I'm going to post this now, but thank you for coming. If there's any interest next week, we haven't done an awful lot today, but trust me, the hardest thing about organic at your level is the drawing of the structures. Okay, because if you can draw the structures, it's really easy. Honestly, 90% of it is drawing, and if you can draw them, you're good. Anyway, guys, we'll have a nice evening. Thank you for joining me. Let me stop the video.